Hello, so let's start our unit on rational equations. Rationals are, if you see the word ratio in the word rational there, a ratio is like a fraction. Okay, so we just finished doing polynomials. Polynomials had no fractions in them. They had nothing on the denominator. They were all just like the numerator part of these equations right here. So rational equations are fractional. Okay, so that's what we're going to study this unit. So here's some examples of rational equations with a numerator and a denominator. A numerator and a denominator, numerator, denominator. Okay, so what you need to know is when you have a fraction, this is very important for this unit, is what can the denominator never, ever, ever be equal to? The denominator can never be equal to 0. So what would make this denominator 0 right here? If you put in 5 for x, the whole denominator would become 0. 5 minus 5 is 0. So that would mean you would have to restrict this equation somehow. At least when you see the graph, you're going to see this on the graph in a minute, is that this equation can never be equal to 5 somewhere. And same with this. What would make this a 0 is if x cubed was equal to 64. So denominator here and here, x would equal 0 here. So you can never have the denominator equal to 0. So x cannot equal 0. X cubed cannot equal 64. What is that? So x can equal 4, right? 4 times 4 times 4, I believe, is 64. And then here, x could not equal to 5. So let's look at a graph of a rational equation. This is a graph here, and we're going to talk about zeros, vertical asymptotes, and horizontal asymptotes. Those are the three components that make up a rational graph. So what you see here is the blue is your function. The blue is your function. These kind of orange lines here are asymptotes. Asymptotes are just, they are guidelines. They are not actually part of your function. They are just guidelines for your function, imaginary lines. So this one, left and right, is the horizontal one. Here, up and down, are your vertical asymptotes. And so we're going to show you here. Here's the x-intercept, or 0. Here's the x-intercept, or 0 here. So what you need to know from this, is that here in the box, very important right here, zeros occur when your function is equal to 0. Okay, so when is your function ever allowed to be equal to 0? Any of these. Can it be 0 in the denominator ever? No. So when your function is equal to 0, that means the numerator is 0. The numerator can be 0, but the denominator never can. So if you have literally a 0 on your graph, that is where the numerator is equal to 0. Okay? So these two tell you where the numerator is equal to 0. So here's just a silly way to remember this. It is 0 over k. It is okay for 0 to be on the top. Okay? 0 can be on the top. Okay. All right. When can it not be 0? On the denominator. So no, NO, right, is when you have a 0 on the denominator, the bottom. Okay, so this is where we're leading with the next one. The VA stands for vertical asymptote. So the vertical asymptotes, where do they occur? That is when the denominator is equal to 0. So vertical asymptotes, what they tell you is when the function is not defined. It is undefined, and therefore the verticals tell you where there are zeros in the denominator. This is where your function is undefined. It's not allowed, right? Right here and right here. So you have two places on this particular function where the denominator would be equal to 0 at x equals -1 and x equals 2. Those are very tiny numbers there. All right. So we're going to recap all of this and put it together here in a minute. So zeros tell you, right, the literal x-intercepts tell you where the zeros on the numerator is, and the verticals tell you where your function equals 0 on the denominator where it's not allowed, right? So you can never, ever, ever, your function should never, ever cross a vertical. Never, ever. It can cross a horizontal anywhere in the middle, but the horizontal is telling you the far right and the far left end behavior, right and left end. See how both of the functions go towards the horizontal on the far right and the far left. Okay, so in the middle, we don't care. It's not about middle behavior here. Horizontals determine end behavior. Verticals, you can never cross. All right. So horizontal asymptote, there's a lot of notes here. You can read these. You can pause if you want to read them. This is how we are going to determine horizontal asymptotes right here with using limit notation like you would in calculus. Okay, so what you want to know is how your function, remember, horizontal asymptotes determine your end behavior. So what we want to know as x's are approaching infinity, what is your horizontal asymptote doing? How is your function behaving as your x's get really large? Okay. So in this case, we are going to do 3 different cases. Today, we're just going to look at one, which is when you have the same degree overall in the numerator as you do overall in the denominator. Okay. So I'm going to show you a couple of examples of this here in a second. So here's your equation. So you're going to get the linear factors from your zeros on the graph, the x-intercepts. Then you will get the linear factors from the vertical asymptotes. Those are going on the denominator. And you're going to multiply everything by the horizontal asymptote that you see on the graph. So let's do an example here. Let me show you first how to do the limit notation, and then we'll put this together with a graph. So let me show you. Let me go to my document camera here. So let's just recap again. Okay, rational equations, they are fractional. The numerators determine where your x-intercepts will be, if any. Okay, denominators are going to tell you where your vertical asymptotes will be. Okay, so remember, you can never, ever allow the denominator to be equal to 0, which means the vertical asymptote will never, ever be crossed by your function because it's not allowed. Okay, that's forbidden zone. Okay, so let's just look at this function right here. So here's your definition for a horizontal asymptote. This is a very formal definition. Basically, what the horizontal asymptote is when you have the same degree of your numerator and denominator, that's the coefficient of your function, the coefficient. All right, but we're going to determine that using a very formal definition here with your limits. So here's your function. Say this is your example function right here, okay? This right here is your coefficient. Put it in the end, don't know why. Could go in the front there too, okay? This is your coefficient. This is what should end up to be your horizontal asymptote in the case of the same degree as the numerator and denominator. So let's look at the degree of the numerator. Multiplicity of 1, overall degree of 2. Here, multiplicity of 1, overall degree of 2. So overall 2, they have the same degree, numerator and denominator. So this is what should be your horizontal. So let's do it with the limit definition. I put the 3 halves here in front, okay? So numerator, denominator, numerator, denominator. Okay, so what is happening here? As your x's get really, really large, infinity, right? When you are talking about, let's put infinity for the x here, right? The x's are going towards infinity. If x is equal to infinity, does infinity plus 3 make any kind of sense whatsoever? Not much. The plus 3, excuse me, that's my favorite friend that keeps popping up. Okay, so plus 3 when you're talking about infinity is like you can just pretty much disregard it. Okay, infinity plus 3, so let's just get rid of that. How about infinity minus 4? Is minus 4, when you're talking about infinity, is that significant? No. Let's get rid of that. How about infinity plus 1? Not very important, right? Infinity minus 2. The minus 2, who cares when you're talking about very, very large numbers? So we can get rid of those. Those are not significant anymore. So what you have is x times x, which is x squared, and down in the denominator, x times x, which is also x squared. And there's your 3/2 sticking out there in the front, okay? So x squared over x squared, what happens to those? They kind of cancel out to 1, right? Reduce to 1, and you're left with 3/2. So do you see how that works? So let's do another example over here. Let's do one more example with that. Let's write that down. So here's another function here. Okay, let's look at the overall degree of the numerator, which is 1, 2, 3. What's the overall degree of denominator? 3. Okay, this is in two different forms, right? This is standard. This is linear factor form, but they still have the same overall degree, 3 and 3. So using your limit notation, the limit of this whole function as x's get very large. So put in infinity here. Infinity minus 2. Do you care? Minus 2, really? Does that play a major role when you're talking about infinity? No. Okay, so you can get rid of that. How about infinity plus 1 plus 1? Who cares, right? Same with this. Infinity cubed minus 64. Who cares about a piddly little minus 64 when you're talking about infinity cubed, right? So this all reduces down to 3 times x squared times x, right? This is still, right? You got rid of the negative 2. That's x squared still. X squared times x over x cubed. This is x cubed divided by x cubed. You can get rid of those, and you are left with 3. Okay? So now I would like to talk about a multiplicity of terms. You know the numerator that always follows the multiplicity like it did with polynomials. If it bounces on the x-axis, it's got to be even multiplicity, and if it passes through the x-axis, it's odd multiplicity. Let's talk about multiplicity for the denominator, which is vertical asymptotes. So yes, there is such a thing as a vertical asymptote bounce or even multiplicity, and a vertical asymptote pass or odd multiplicity. So let's look at the first one, which is the even multiplicity. Just hang on, and we'll put this all together in 1 second here, okay? So here is a vertical asymptote. So when we're talking about a vertical bounce, I want you to just look at the graph that's immediately surrounding the vertical asymptote. If both ends of your function are pointing in the same direction, both down, see, here's your vertical asymptote. Both of these parts of your function are pointing in the same direction, both down, or if they were both up. That would be an even multiplicity for the factor, this vertical asymptote factor in your denominator. Okay. Here's another example over here with this graph right here. Okay, there's a rational function. I threw one at you there. Just look at this vertical asymptote right here, right here. On either side of that vertical asymptote right there, this is your function. Both ends pointing up, they're both going in the same direction around that vertical asymptote. This would be a vertical asymptote bounce. Okay, that means at whatever this vertical asymptote is here, this would have an even multiplicity in your denominator. Okay. Now let's talk about the other one, which is a pass or odd multiplicity. Let's look. Here's your vertical asymptote here. So if you just look at what your function is doing, on either side of that vertical asymptote right there, one end is pointing down, one is pointing up. That would be odd, right? They're both pointing in different directions. That would be odd multiplicity of this vertical asymptote in your denominator. Here's another example here, right? I did it on this one. Here, that's even. They're both pointing up. Look at this one. There is odd multiplicity with this one because they're pointing in different directions, your function, around that vertical asymptote right there. Okay? So again, the horizontals determine your end behavior. Look at the far left, the far right, the far left, the far right. Same with this one. Far right, far left. Look how your graph is always going towards the horizontal at the far ends. Okay? It doesn't matter in the middle what's happening with horizontals. Your function could cross over it in the middle part, but the ends should be following your horizontals. The verticals, however, your function should never cross over that. Never, ever. Okay? So let's do one easy function here. Let's put this together here and write the function from the graph. There's where we're going. Just like we did with polynomials, we're going to be able to take a graph and write a function, or the other way around, take a function and draw the graph. So we're going to do this one example, and then I'm going to go to part 2 after this. So here you go. You've got, this is your function. Here are your zeros. Here is a vertical asymptote. Here's a horizontal asymptote. So the numerator is determined by your zeros. So here's your 0 at x equals 1. So I'm going to write one linear factor, x minus 1, x minus the intercept. Here's the other one, x minus the intercept. Okay. And then I'm going to do the denominator, which is determined by, oh, I didn't give that a value. Let's say that's, right, let's say that's x equals 2. I'm just making up a number, okay? So here's your vertical asymptote. That determines your the denominator down here. So if that's at x equals 2, right there, if that's 2 right there, this would be x minus that number. And then because if you look at this, both ends of your graph are pointing upwards around, they're both pointing in the same direction. That's all that counts, same direction. You would have a vertical bounce, which would mean it would have to have even multiplicity at the very least. Okay. And now from all we know so far, you've got a horizontal asymptote as well. If that's the case, for all we know, both the left and the right ends are following this horizontal asymptote, but that also means that the numerator degree has to match the denominator degree. So look at the degree overall of the numerator, 1, 2, and here in the denominator 2. So degree of numerator equals degree of denominator, which means we have this horizontal asymptote. What is that number telling you? If this horizontal asymptote is at y equals -2, that means that's the coefficient of this function right here. So now you just completed a function. You wrote it from this graph right here. If I were to formally check, just double check the horizontal asymptote there, you could take the limit of this as x approaches positive infinity of -2, the entire function, x minus 1, x minus 9, all divided by x minus 2 squared. Remember, this -2 out there is the same as -2 over 1. So it really goes here in the numerator. You can also plunk it out there in the front if you wanted to, okay? But it's really there in the numerator. Okay, so what's happening is x's get really, really large. If x is really large here, this -1 is like Insignificant. Same here, -9, insignificant when you're talking about infinity. So is -2 there, -2. So what you're left with is -2 over x times x, which is x squared over x, right? X squared down there. Those two reduce to 1, and you're left with -2, which is, yes, that's your horizontal. I just double checked. Okay, that's all that is. What you would normally have to do, take the graph and write the function that way. All right, thank you. I'm going to do another video after this. Thank you very much.